Hello friends, I welcome you in lecture number 13 on residues. In this lecture we are going to discuss one problem on Cauchy's residue theorem which was asked in GTU winter 2020 exam. So let's try to evaluate this complex integral which is asked to evaluated using Cauchy's residue theorem. So here function is 5z minus 2 divided by z times z minus 1 and simple closed contour is circle with center origin and radius 2, that is mod z equal to 2. So first we denote our function by f of z. Let f of z equal to 5z minus 2 divided by z times z minus 1. So this function is rational function. It is division of two polynomials 5z minus 2 and z square minus z. Okay, denominator can be written as z square minus z, which is polynomial of second degree, and we know that polynomial functions are analytic everywhere. So f of z is not analytic at those points for which this denominator becomes 0, that is this is 0 if z equal to 0 and z equal to 1. So z equal to 0 and 1 are the only points at which this function is not analytic. So we can write that clearly f of z is analytic everywhere except z equal to 0 and z equal to 1. So these two are isolated singular points of f of z. Therefore f of z has isolated singular points at z equal to 0 and z equal to 1. Now given simple closed contour is circle with center origin and radius 2. C is represented by mod z equal to 2. So if we consider circle with center origin and radius 2, suppose this is this circle with center origin and radius 2. Okay, this is just for understanding, you need not sketch the circle. So suppose this is circle of radius 2, so this is approximately 1, this is 0. Here also we have 2. So this is real axis, this is imaginary axis. So f of z has two isolated singular points, z equal to 0 and z equal to 1, and both are inside this simple closed contour mod z equal to 2. So we can say that f of z is analytic everywhere on and inside this simple closed contour C except 2 points z equal to 0 and z equal to 1, which are inside this circle mod z equal to 2. So hypothesis of Cauchy's residue theorem is satisfied. We require that f of z is analytic everywhere inside and on C except finite number of points, which are 2 here, z equal to 0 and z equal to 1. So we can apply Cauchy's residue theorem to evaluate integral of this function f of z along this circle. So for Cauchy's residue theorem, we require residues of f of z at z equal to 0 and at z equal to 1. So we calculate residues one by one. First we calculate residue at z equal to 0. For that we write our function first, which is 5z minus 2 divided by z times z minus 1. So this we can rewrite as, I consider 5z minus 2 divided by z minus 1 in the numerator, and I keep z here, and this numerator I denote by function of z denoted by phi of z. This we can rewrite as z minus 0 to the power 1, where this phi of z is nothing but 5z minus 2 divided by z minus 1, and this is clearly analytic at z equal to 0, which is analytic at z equal to 0. This phi of z is not analytic at z equal to 1 only, so it is analytic at z equal to 0, and value of phi at z equal to 0 is, we substitute z equal to 0 here, so we have 0 minus 2 divided by 0 minus 1, that is minus 2 divided by minus 1, which is 2, and it is non-zero. So f of z is expressed in this form, phi of z over z minus 0 raised to 1, where this phi of z is analytic at z equal to 0 and value of phi at z equal to 0 is non-zero. So therefore, because here power of z minus 0 is 1, we can say that z equal to 0 is a pole of order 1 of this function f of z, or we can say that f of z has a simple pole. Pole of order 1 is known as simple pole. F of z has a simple pole at z equal to 0, and residue of f of z at z equal to 0 will be equal to value of function phi at z equal to 0, which is 2 here, and suppose we denote this residue by capital B suffix 1, so suppose b1 equal to 2. Now we calculate residue at z equal to 1. Same method we will apply. Here we require residue at z equal to 0. For residue at z equal to 0, we consider this part in the numerator. Now for residue at z equal to 1, we will consider this part in the numerator. So we rewrite our function f of z as f of z equal to, we keep z minus 1 in the denominator, and 5z minus 2 divided by z, we write it in the numerator, and we denote this by phi of z divided by z minus 1. Here power of z minus 1 is 1, and where phi of z is now 5z minus 2 divided by z. This phi of z is analytic everywhere except z equal to 0, so it is analytic at z equal to 1. This is analytic at z equal to 1, and value of phi at z equal to 1 will be equal to, we put z equal to 1 here, so 5 into 1, that is 5 minus 2 divided by 1, which is 3, and it is non-zero. So here also f of z is written as phi of z divided by z minus 1 to the power 1, where phi of z is analytic at z equal to 1 and value of phi at z equal to 1 is non-zero. Therefore, this z equal to 1 is a pole of order 1, because here also power of z minus 1 is 1. So therefore, z equal to 1 is a pole of function f of z of order 1, or f of z has a simple pole at z equal to 1, and residue of f of z at z equal to 1 will be value of function phi at z equal to 1, which is 3, and we denote this residue by b2. So we have obtained residues of f of z at both the isolated singular points which are inside this simple closed contour C. So now we can apply Cauchy's residue theorem to evaluate integral of f of z along given contour. So now by Cauchy's residue theorem, integral of f of z along given contour or given circle mod z equal to 2 2 pi I times sum of residues of f of z. Residues of f of z are denoted by b1 and b2. So sum of b1 and b2. So we substitute values of b1 and b2. b1 is 2 and What is b2? b2 is 3, so we have 2 plus 3. So let me rewrite this bracket. 2 pi I times 2 plus 3, okay, so that is 2 pi I times 5, that is 10 pi I. So therefore integral of 5z minus 2 divided by z times z minus 1 with respect to z along simple closed contour, which is mod z equal to 2, is nothing but 10 pi I. So in this way it is easy to evaluate complex integrals using Cauchy's residue theorem, but for that our function must satisfy hypothesis of Cauchy's residue theorem. In Cauchy's residue theorem we require that given function is analytic everywhere inside and on a simple closed contour C except finite number of points. And one more thing which I am always repeating, to find out residues we are using this result, that if our function can be written as phi of z divided by z minus z0 to the power m, where phi of z is analytic at z0 and phi of z0 is non-zero, then f of z has a pole of order m. If f of z can be written in this way, phi of z over z minus z0 raised to m, where phi of z is analytic at z0 and phi of z0 is non-zero, then this power is order of pole. So this z0 is a pole of order m, or f of z has a pole of order m at z0, and if f of z has a pole of order m at z0, then residue of f of z at z equal to 0 is given by this m minus 1th derivative of this function phi at point z0 divided by m minus 1 factorial. And if we have simple pole, if order of pole is 1, then residue will become value of function phi at z equal to z0. So residue of f of z at simple pole is nothing but value of function phi at z0. That we can see from this also. If z0 is a simple pole, we have m equal to 1. So if we put m equal to 1, we have 0 derivative of phi divided by 0 factorial. 0 derivative of phi means function phi itself, and 0 factorial is 1. So in this way we can evaluate some complex integrals using Cauchy's residue theorem, provided whatever function is given, that function satisfies hypothesis of Cauchy's residue theorem. So this is all about today's session. I hope you like it. Thank you very much.